In this screencast, we're going to talk about oxidation reduction reactions. These are sometimes called redox reactions. This is the only type of reaction we're going to talk about in this screencast, and has quite a few applications when we think about cosmetics chemistry. Let's talk about, we're going to define some terms first. So when we have oxidation reduction reactions, we have an atom that will lose an electron and an atom that will gain an electron. So basically, this type of reaction is a transfer of electrons. So atoms that lose electrons during the reaction are said to undergo oxidation. Okay. And so when we talk about that, and I'm going to kind of color coordinate here, right? We have oxidation happening here, which is electron loss, right? And so that atom that was oxidized, right, is now over here, right? It's got one fewer electron. Now, it gives that electron to the thing it reacts with, which, and we say that is reduction. Okay, and so you can see, right, that when we have this electron here and it's given to this guy here, that's reduction. It has gained an electron, right? So now this new species has the electron on it. What makes this somewhat complicated is that there's some other terms that describe what is being oxidized and what is being reduced. So the oxidized species that I have there in blue, right? It can also be called the reducing agent. And you see that right here, okay? So we've got the oxidation here, and that thing that undergoes oxidation, right, that chemical is the reducing agent. It causes the reduction of the other thing. That's why it's called the reducing agent. Now in cosmetics, more often, this is called an antioxidant. Okay, and so you'll see the term oxidation, reducing agent, and antioxidant used to describe almost the same chemical compound, right? And so sometimes that can throw students off. Now, same thing, the reduced species is called the oxidizing agent, which is also known as the oxidant, right? And here is that oxidizing agent. When we talk about the oxidizing agent, it is the thing that is reduced. It's the thing that undergoes reduction and it causes the oxidation. In cosmetics chemistry, a lot of times that's referred to as an oxidant. So that's the thing that goes through reduction. So I've got those color coded here for you. So that can be kind of complex and confusing, and so I wanted to make sure that we were pretty clear on that. I want to do a few examples of us recognizing if things are reduced or oxidized. So, for example, we are going to look at something called half reactions. These are just reactions with one species, and what you do is you compare the reactant with the product. Okay, and so when we're looking at this to figure out if something has lost or gained an electron, it's helpful to look at the charge. Okay, so when we look at magnesium here, we see the charge on magnesium is +2 in the reactants. When we go over and we look at magnesium in the product, it doesn't have a charge there. And so if it doesn't have a charge, if it's all by itself, it means its charge is 0. Okay, it doesn't have a +1, it doesn't have a -1, it's 0. So let's think about what's happening with magnesium here. It's going from a +2 charge to a charge of 0. This means to get from a +2 to a 0, it had to gain 2 electrons, okay? And so if it's gained electrons, it underwent reduction. Okay, so this gained electrons, it has undergone reduction. Another way we can say that is it's been reduced. That's what we see there. So sometimes we can see these little half reactions. Let's look at another example. We have iron, that's a solid. And it goes to iron 3 plus, which is aqueous. So we have a 0 here. Sorry, I wrote that above. So our charge here with iron is 0, and it goes from 0 to plus 3. And the plus 3 that's given on that complex is how we realize that's a plus 3 charge. So to go from 0 to plus 3, it has to have lost electrons. Electrons are negatively charged. If you lose 3 electrons, you now will have a positive charge. So it's lost electrons, and so it has been oxidized. So it's undergone oxidation, okay? Now, I want us to look at, so these are little half reactions we've looked at, but I also want us to look at some examples of full reactions and figuring out the charges there. One thing to be aware of is that oxidation and reduction reactions are always coupled. If you have one, you have the other. A really good way or a mnemonic to help us remember which is oxidation and which is reduction is oil rig. Oxidation is the loss of an electron and reduction is the gain of an electron. So I want us to do some examples here, identifying oxidation and reduction in some chemical reactions. So the first example, I want us to take iron oxide, and this can react with hydrogen gas to form solid iron and water. Now I'm going to leave out the states just for simplicity, okay? So when you're trying to figure out what's being oxidized and what's being reduced, the first thing you want to do is assign charges. So you need to go through and you need to assign charges, okay? And so anything that's by itself is 0. So the hydrogen here is 0, the iron here is 0. Now, we have iron oxide. Iron oxide, there's no charge that we can see. And so what we have to do is we have to figure out the charge on the iron like we did when we were naming ionic compounds that had Roman numerals, okay? Oxygen, we know oxygen has a -2 charge. We can see that from the periodic table. There are 3 oxygen atoms there, right? So -2 times 3 gives us a total of a -6 charge. There are 2 irons here. So to figure out the charge on the iron, we take the -6, we divide it by 2, and that gives us -3, right? And so the iron has to cancel out a -3. So that means that iron's charge right here is a +3, okay? So iron is a +3, oxygen here is a -2. Now, when we go over and look at oxygen here, oxygen's still a -2. There are 2 hydrogens there. This overall complex doesn't have a charge, so that means those 2 hydrogens must have a charge of +1 to cancel out that -2. So here we have our charges. We are going to ignore oxygen. The charge on oxygen doesn't change, so it is not being oxidized or reduced. So we need to focus on the things where the charges change. So let's look at iron, right? Iron is going from a +3 to a 0. When it's gone from a +3 to a 0, the only way it can do that is it can gain electrons. So it's gained 3 electrons. And so if something gains electrons, it's being reduced. Okay, so that means iron's being reduced. That also means that Fe2O3 is the oxidizing agent. Okay, that's the thing that is causing the hydrogen gas there to be reduced, basically. So when we think about hydrogen, hydrogen is going from 0 to +1. That means it's lost an electron. So that means it has been oxidized because oxidation is the loss of an electron. So it undergoes oxidation. And that also means that H2 is the reducing agent. Okay. Let's do one more example. And in this example, if you wanted to, you can you could pause the screencast and try it on your own and then come back and check the answers. So when we look at this, this is a synthesis or a combination reaction. We come here and we say, okay, copper is all by itself, so it has a charge of 0. Oxygen's all by itself, it has a charge of 0. Now we have copper oxide. Oxygen from the periodic table, we know its charge is -2. Copper from the not from the periodic table, but because it's complexed with oxygen, and there's only one of them, and whatever charge copper has, it has to cancel out oxygen's charge, is going to have a +2 here. So when we look at copper's journey, it goes from a 0 to a +2. And so that means it has lost electrons, right? And so that means it's oxidized, or it's gone through oxidation. And so it is the reducing agent. Then we also have oxygen here. Oxygen goes from 0 to -2. That means it has gained electrons, and so it has been reduced. It's also called the oxidizing agent. Okay. So we have done 2 examples where we have identified chemical species that are oxidized or reduced. Where do we see this in cosmetics? Well, we see it mostly when we talk about pigments. So if you look here, we're talking mostly about ionic compounds. In general, pigments are generally ionic compounds. Okay. And they give a product color. And these are sometimes referred to as inorganic substances because they're compared to organic dyes that can also be used to give things color. We're going to have a color module later in the course where we'll talk about some of the science behind colors in pigmentation and cosmetics. This is an image that I grabbed from TKB Trading. They are a cosmetics trading company that's located in California. And they sell many oxides that are used for things like lipsticks, lip gloss. They even have some really fun kits that you can order if that's something you're interested in. They also have some eyeshadow kits. And so this is a sampler pack that they have of all of the different colors that you can use to make eyeshadows. Now, that being said, when we look at this, if you want a pigment for an eyeshadow, you do not want it to go through oxidation because oxidation can cause the color to change, right? And so that's not something that we really want. So the goal for your cosmetics a lot of times that have pigments in them is for them not to undergo oxidation, because if they do, then the color can change slightly. So if you've ever used liquid foundation and you color match really well, and then over time that foundation color gets a little off, you could have oxidation occurring. Same thing with your eyeshadows. When I did some brief searches on this, the thing that I found most often that people talked about was iron. Iron complexes are gonna be in your red shades, like here, and your kind of brown shades. So this is where we're gonna see some of those iron oxides. And so if any of the iron oxide complexes, and there's lots of different ones, go through an oxidation reaction, that can shift the color just a little bit. The actual mechanism of this involves multiple redox reactions, and it's honestly highly unlikely to happen in your cosmetics. And if it does, it won't happen for a very, very long time, particularly with eyeshadows, because there's just not a lot of water in them. And so you don't see it very often. But it is worth mentioning because if you kind of search for that, iron oxides are the ones that it brings up most often. Now, more often in cosmetics, we see redox reactions in organic compounds. Now, we are going to do a deep dive into organic molecules in the next module that we do. But it's worth mentioning the reactions, the redox reactions that organic molecules undergo here. When we talk about an organic molecule, in general, organic molecules are covalent molecules that contain mostly carbon and hydrogen. You can also see other atoms like oxygen or sulfur or nitrogen. Those are really common molecules that are in organic compounds. Okay, but they're covalent, so we're sharing electrons here. And instead of looking at the charge, because we don't have any charge to look at for organic molecules, we look and keep track of oxygen and hydrogen bonds. Okay, an organic molecule is oxidized if it gains an oxygen bond or atom, or loses a hydrogen. Okay, so when we talk about this, the other thing to look for is reduction. So I have a kind of nifty chart here for you. So when we talk about oxidation here, which is what this sentence is talking about, we're losing electrons. And what we're going to see in organic compounds is it's an addition of an oxygen or loss of a hydrogen. And if it's loss of a hydrogen, it's the hydrogen atom. With oxygen, it can be a little bit more tricky because you can lose the oxygen atom or just lose an oxygen bond. With reduction, you gain electrons, right? And when we're talking about oxidation, reduction reactions in organic molecules, we are going to keep track of oxygen. And you can either lose an oxygen atom or an oxygen bond, or you can gain hydrogen, okay? So that's what we keep track of. So, for example, let's look at this molecule right here. This molecule is called an aldehyde. We will worry about that in the next module, naming these. But basically what we have here is a carbon that has 2 bonds to oxygen and 1 bond to hydrogen. When it goes through reduction, right, what you're going to see here is that it gains a hydrogen atom, right? So it's got 1 hydrogen, and now we've got 2 hydrogens. The other thing to notice is it's lost a bond to the oxygen. So it had 2 bonds to the oxygen here and only has 1 bond here. It's been reduced, okay? Now, this can also go through oxidation, right? So when we talk about oxidation, it can be the addition of an oxygen bond or atom. In this case, we are adding an oxygen bond right here, like an oxygen atom right here. And so that is oxidation, okay? So those are some ways that we look and can see if organic compounds are being oxidized or reduced, or these covalent compounds are being oxidized or reduced when we don't have the charges necessarily. So we're going to look for those oxygen and hydrogen bonds. Now, one of the things that you may have encountered when we talk about cosmetics is this idea of free radicals. Now, free radicals are going to be a reduced species. Right? They are also known as the oxidant. Now, oxidants are just molecules that are missing 1 or more electron. So this is our free radical. It is an oxidant, and so we've got our nucleus here, we have the electrons here, and we see that it's missing an electron, okay? These can be really damaging to our cells. Our cells produce these just as a byproduct of the production of energy through chemical oxidation. And during this process, we have reactive oxygen compounds that are formed, right? And so some of these free radicals that are formed are things like nitrous oxide, um, hydroxide radical, and an oxygen radical. Now you're going to see this dot here, and this dot means there's a radical. That is an unpaired electron. That unpaired electron there, that's shown there, is the unpaired electron. And they're basically called free radicals because they have this unpaired electron. So they are missing one or more electrons. And because of that, they're really reactive. They really want to gain an electron to become stable. Okay, and so they can react with a stable atom for this to occur, and that's really unfortunate. Because it causes cellular and DNA damage, right? So an overabundance of free radicals can cause cellular and DNA damage, right? And if you look, this is a transfer of electrons, right? So this is a redox reaction, and how this applies to cosmetics chemistry is when you have this cellular and DNA damage, what results here is aging, right? And things like wrinkles, okay, and inflammation. Cataracts and cancer can also occur. And so what we use to defend against these free radicals are antioxidants, right? So antioxidants are our reducing agents that defend against free radicals. So what they do is they come along and they donate an electron to the free radical, right? And it keeps the free radical from reacting with stable ions by reacting with these antioxidants. So we're going to look at 3 common antioxidants that are used in cosmetics pretty commonly. The first one is vitamin E. Vitamin E covers a group of about 8 fat-soluble compounds. So these are about 8 fat-soluble compounds. Okay. These are found every day in oils like olive oil and sunflower oil. They're put into 2 groups. There are 4 tocopherols and 4 tocotrienols, right? So we have 4 and 4. They're commonly found in olive and sunflower oil. The structure has an impact on how body and skin interact, and how our body uses them. This top structure here is alpha. Now you can see alpha written out or alpha drawn like this. And it has the greatest bioavailability, which means it's very easily absorbed and used by the skin. So of the 8, this is the one that has the greatest bioavailability. Right? So that means it's very easily absorbed. Right? And used by the skin. Okay? And it tends to have a greater presence than all the other ones. when we talk about vitamin E. So this is the vitamin E that you see most commonly. Um, Now it protects. So the way vitamin E works is it protects the cell membranes in our skin by stopping the production of those free radicals. And those free radicals, of course, attack and break down our cell membranes, resulting in aging of the skin. Okay, so the free radicals here are what attack and break down our cell membranes, and that results in aging of the skin. I feel like I misspelled aging. Let me put that E in there. Now, the stability of the alpha tocopherol is uh, sometimes not as stable as people would like when they're doing cosmetic formulations. And so instead, what's added is alpha tocopherol acetate. If you compare these two structures, the only thing that is different, right, is there's a hydroxyl group, which is an OH group right there, right? And then right here, there's an oxygen with a double bonded oxygen to another carbon, right? So it's just got that group on there. And this will be absorbed by the skin, and then it's converted to this molecule here. So sometimes you'll see this on packages with vitamin E in it because it's absorbed by the skin and converted to this in the skin. So it's in a lot of skin creams. Okay, so vitamin E is our first really common antioxidant. I want to point out something here. I want to remind you that at each of these little places where these lines meet, those are carbons. This is mostly a carbon complex with just two oxygens, and so that means it is nonpolar. So this is a nonpolar molecule, and it's one of our fat soluble vitamins. Okay, so when we talk about vitamin E, that's one of our fat soluble vitamins. When we talk about fat soluble vitamins, there are 4, A, D, E, and K that are commonly the fat soluble vitamins. The next antioxidant that we have is vitamin A. That's also a fat soluble vitamin. The term vitamin A covers a group of molecules that are all derived from retinol, which is a chemical converted from beta carotene. So when we look at beta carotene here, you may have heard of beta carotene. It's found in carrots. It makes carrots orange, right? And and retinol is a derivative of that. So ignore these numbers. I like this image because it shows you both retinol and beta carotene. And basically you can see where it's divided here. The mechanism for how we get from beta carotene to retinol is quite complex. So we're not going to talk about that, but it's just that's where retinol comes from. So when we talk about vitamin A, it's converted from beta carotene. Now, that conversion of when we talk about a conversion of retinol, it will be converted from retinol to retinoic acid in the skin. And what that does is it aids normal skin development. Right? Now, it helps increase the collagen and elastin content in the skin. Right? And so what that does is it leads to a reduction in the appearance of fine lines and wrinkles. Okay. It also helps improve the elasticity of the skin. Right? Now, retinol is also known to reduce discoloration and improve skin tone. So it helps reduce discoloration, which are things like age spots, right? And improve skin tone. And it does this by interacting with melanin, which provides the color to the skin. So there's a couple different mechanisms for this. It helps the skin cells turn over more, which is one of the things that helps that regulate that color a little bit better. So if you've seen somebody who's a lot older with kind of some of those dark age spots, that's one of the things that is commonly used as vitamin A. It is also fat soluble. Because it's mostly carbons and hydrogens with only one oxygen. So it is a fat soluble vitamin. Another oxidant that we run into is vitamin C. Vitamin C is also known as ascorbic acid. When we talk about vitamin C, it's present in the skin as the skin's own defense against oxidation. Now, it is water soluble. Okay, so it's not one of the fat soluble vitamins. And vitamin C is pretty easily lost from the skin when it's exposed to any stresses or sunlight. And so replacing the lost vitamin C is really beneficial for your skin's health. Now, vitamin C sometimes is a little bit unstable. And so what people put into cosmetics instead, a lot of times, is sodium ascorbyl phosphate. Right? And that is a stable form of vitamin C. And I have a image of the structure here, right? So this is the sodium ascorbyl phosphate. You can see the phosphate group here, like the polyatomic ions that we talked about, and there's your sodium. And it's just complex to the vitamin C. So you can compare the structure here to the structure here. It's just less affected by light and air. And on application, is converted to ascorbic acid. Right? And it's that form that's mostly used in cosmetics. Now, vitamin C is used for skin lightening. Right? It's an anti-acne, and it enhances skin firmness, through stimulation of collagen production. Okay. So those are 3 antioxidants that are commonly used in anti-aging cosmetics. But as we mentioned at the beginning, oxidation a lot of times is a problem in cosmetics. You don't want a chemical in a cosmetic to undergo oxidation because when it's sitting on the shelf, because it will lose its effectiveness. And so a really good example of that is vitamin C, is ascorbic acid. So we talked about vitamin C, and vitamin C can undergo oxidation. And so here's our ascorbic acid, also known as vitamin C, it can undergo oxidation. And when we look at the oxidation, what's happening here is if you look at this OH, right, we lose that hydrogen and we gain a double bond there, right? So that's the oxidation process it goes through. And this, you can see this in some vitamin C products. And so a really good example of that is Drunk Elephant. So Drunk Elephant is a skin line, and they have a C Firma Fresh Day serum. And when we look at that, it's got ascorbic acid in it, right? So when they first came out with this particular product, it was shipped to you as a liquid, right? And it was shipped to you as a liquid, and this is the color. But over time, it undergoes oxidation and it changes colors. Now, this is a problem in cosmetics for a few reasons. Even though there are some studies that show that when it changes colors, it doesn't really affect how the vitamin C works with your skin. Just honestly, consumers don't like it. They don't like when something has changed colors. It also smells a little bit, and so they don't love that as well. And so this was a real problem for Drunken Elephant. They couldn't keep these on the shelves because, as you can imagine, if you bought one of these and that was the color when you first started using it, right, you'd be a dissatisfied customer. So the shelf life wasn't very good here. And so what they did is they changed it. So now when you get this product, when you buy this product, they have the powder in here, and you add the liquid water to it, and you shake it up and you make the solution. And so that helps extend the shelf life so that when you have this product, basically the oxidation timer starts when you add the water to it. And so it was a really nice way to get around this problem of oxidation with their products. So oxidation in cosmetics can be a problem. The other place that we see oxidation in cosmetics is in henna tattoos. So when we talk about henna tattoos, the henna plant has an active ingredient called lawsum. So if we have a henna plant, right, that active ingredient is lawsum, right? And that molecule is also called 2-hydroxy-1,4-naphthoquinone, right? Oh, my O and my Q overlap there. Just ignore that. And this is that molecule, right? So we've got that molecule right there. So it's extracted from the plant and mixed with like essential oils and a paste, and it can be applied to the skin. When it's applied to the skin, it's a particularly fun product, right? It will complex with the keratin in the skin. It's interesting. I've read about this from two different sources. One source says it combines with the amine group. One source says it combines with the sulfur of the keratin. We're going to go with the sulfur of the keratin here. I'm sure there's some that combines with the amine group as well. But it combines with the sulfur group here to form a bond, right? And so over time, right, what happens is that complex that's bonded to keratin, right? So there's the henna, right? There's that molecule. It's bonded to keratin. Over time, about 10 hours, it will undergo oxidation and it will darken on the skin. And so what we see as it undergoes oxidation is, again, we've got this OH group here and we've lost a hydrogen and we've gained a carbon to oxygen bond. And that's that process of oxidation. And when it does that, it darkens, right? And so it will leave a lasting impression, kind of like a temporary tattoo on your skin. So, right, that's how henna works, is by using this idea of oxidation. This particular type of henna is called red henna, right, which is 100% the lawsum, that henna product. You do have to be careful if you see black henna. Black henna, the reason you need to be careful is it may contain a chemical called paraphenyl diamine, right? Which is abbreviated as PPD for short. And it can be mixed with red henna or sometimes indigo, right? And it produces a really nice black. The problem is that it is a potent contact allergen. So, and it's also banned in Europe and North America. So if you are in a place and they are advertising black henna as opposed to kind of this red henna, and you can't see the ingredients where it says 100% henna, you do need to be very, very careful, because that's a contact allergen that will develop once, hours after having it on your skin. So you can get the henna and then you can walk away, and then 24 hours later, now you have an allergen issue. So you do have to be quite careful about that. If you are getting henna in the United States, you shouldn't run into that, because this has been banned in henna. But it's just kind of interesting. But yes, henna also works through using redox reactions. All right, so this ends our screencast on redox reactions. We will work on identifying redox reactions more in class. As always, if you have any questions, please feel free to stop by my office.